Salvete amici. Ora decima antemerdium est Redmondi et tempus iterum est pro .NET API review. If anybody actually speaks Latin, my pronunciation sounded more Italian, so yeah, let me know. All right, once again we have a scroll bar. Once again we have ambitions of not having a scroll bar, but we'll see how we do. All right, first up, we have new user-defined operator names. .NET Runtime 114930. Alexi.
Yeah, basically in C# language, we start supporting new forms of user-defined operators. Specifically, these are instance operators versus like static methods. And basically, these are increment, plus plus, minus minus operators, and the compound assignment operators. So, and we need some names to be blessed for to use for the methods that implement the operators. So some of them already are part of the ECMA spec and already listed as reserved, but some are still missing. Like for example, um, yeah, so we need specifically for increment and decrement operators, we need a distinct name from just open the score decrement or open the score increment. Those are already reserved, but we run into some issues with interaction with other features in C Sharp. So, and it would be good to use distinct names for instance forms of this operator. So, and we are proposing like simply adding an assignment as a suffix to already used names, like already used name is open the score decrement, open the score increment, open the score checked decrement, open the score checked increment. And so for new operators, we just propose to add four new names, which basically adding the assignment suffix that sort of gives you an indication that these are instance operators. They are supposed to modify the instance itself versus like calculate something and produce a different result. So, and if you scroll down, yeah, oh, not that's too much. I mean, the second table, yeah, stop. Um, okay, looks like I'm missing some names. Um, Let me take a look at the issue myself. Just give me a moment.
I think the general summary is we've got some existing ECMA names like op edition assignment, and
Oh, right.
we want to go and extend and define the checked versions of these, just like we did for checked arithmetic in .NET when we introduced generic math. And so the convention for the checked variant was to put checked before the name. So we went from op edition to op checked edition. In the same way, we want to go from op edition assignment to op checked edition assignment. And then for increment and decrement, we want to have the assignment version as well for the instance functions. And so those are following the convention of putting assignment as the suffix.
Yeah,
I
but that's
think it.
not actually the convention. The convention is put assignment as the suffix when the operator ends in an equals.
Well, that's the C sharp operator. Not all languages use that syntax for assignment operations.
Fair enough. But from the C and C sharp operator semantics, the operators that we call assignment are the ones that end in equals.
Yeah, but plus plus and minus minus are also assignment operators. They expand into x equals x plus 1 effectively. There's a bit more nuance than that, but that's how they operate. So they are assignment operations.
Sure. Except I think the static ones are you're just supposed to return x plus 1 or x minus 1, and then the assignment is implicit in the language.
Yeah. But then this is for the ref for the instance variant, which takes a
Sure.
ref and therefore is doing self-assignment rather than returning.
There is a precedent of using assignment word. So basically, there is already open the score addition assignment. There is already open the score subtraction assignment and whole bunch of similar ones, right?
Right. I'm just. It's.
So
Do we want to
so
use
so
assignment
so
or do we
which
want to use
so
like
just a moment.
self?
So just a moment. Let me finish, please. Uh, so what we are missing is the checked version of those, because the C# supports checked versions of those operators. It supports checked version of other like regular binary operators and what would look like addition. Then there is a checked addition. So when we were implementing the checked operators previously, like several releases ago, how we arrived to checked to names for checked flavors is like adding checked after open the score to the existing name. So that's why the last four names, this is how those names basically came into existence. There is already open the score addition assignment. We need a checked version of it. So we simply added the checked as a prefix essentially. So that's how they and if you look at the ECMASpec open the score addition assignment is specifically for plus equals. So I'm not sure what the concern here about using the assignment word for those. Like I
There
can
isn't one.
see, I can see how that might be, that there might be concern about decrement and decrement.
Yeah, that's the only thing I'm
But
talking about.
yeah, but we felt that they are pretty much very similar in terms of their semantics. They are assigning to the instance to which the operator is applied to. So, and by basically similarity to the compound assignment operators, we decided that just adding assignment suffix to differentiate feels like a reasonable um,
Yes, and that's what I would like to
thing to.
discuss.
Yeah, sure. Yeah, let's.
I don't think anyone's going to have any concern with the insertion of checked to the checked operators. If anybody
Cool.
does, speak up. Okay. So the I think the only thing about this that rubs me the wrong way is the use of assignment for the self-modifying when it's a new use of it is a new interpretation of the assignment suffix on these operators. And so I am simply wondering, do we want to use a different word such as op self-decrement instead of decrement assignment?
So I'm not sure that it's really different, especially when you consider how C++, which is the language that already supports the assignment operators today, uses it. So C++ defines their assignment operators as instance methods. And so they're all self, and as the only language that really largely supports it before C# starts adding it. So the assignment already largely means self.
Right, but we already did it differently. So we need to reconcile our differently universe.
Well, to be honest, specification doesn't prescribe what the operator does and really doesn't really. Uh, I think it doesn't even prescribe the signature of the operator and whatnot.
Right.
Um,
So why is it important that it's instant? Sorry, maybe I missed that. Like, because if it was static, you could still mutate, right? Like, if you really wanted to. Is it? Are we worried about
No,
like?
because for structs you can't.
I see.
because
For
you
sure.
have to take the first parameter by
Of
rep so
course.
that it can do the self mutation.
I see, but you
So,
could do that, right? You could do static rep, I suppose.
well, for example, consider the following scenario. You are defining an interface and you want to add this mutating operator on the interface. You have no idea what type is going to implement the interface. So suppose we say, okay, you need to define it in static form. So what, like, are you supposed to use ref, or are you supposed not to use ref, or are you
I see. So it is
simply,
for virtual
or
dispatch.
are you
Like that's
simply
a
go,
goal.
or are you simply saying that you cannot define those in interface because you have no idea what type is going to implement the interface? So, and there are other considerations like that, like um, like for example, who is responsible for producing the result? Like, are we supposed to trust the method to return, like static methods, static, like if you look at the signatures of static operators, they return the result essentially. So you're suggesting that we might add a static operator like increment that takes the target and returns the result. At the same time, it's supposed to um, basically modify the target. So are we supposed to trust the implementer that it does the right thing? And why would we want to do that where there is a very clear contract? It's a study, it's an instance method. It gets invoked on the instance. Instance is getting modified. The instance is the result. We don't basically duplicate any, we don't introduce any confusion. What comes in, what's the result? That's why we as a language decided that the right way to implement or to define those operators to do this with instance methods that return void even. The target is the instance on which the operator is invoked, and it's not supposed to return anything. The only thing that this method is supposed to do is to properly adjust the instance according to the rules of the operation, basically. And it's the responsibility of the compiler to produce the result. Basically, this sometimes result is not used and compiler doesn't care what the result is, basically. In cases when there is language in the language you are using the result, for example, you use I++ as an argument in a method call, for example, then language simply produces the target instance as the result. That's it. So that's why we feel like the most appropriate and cleanest design for those is instance methods, not some form of wacky static methods.
Yeah, that makes sense to me. I was just like curious whether like virtual dispatch is like something that we wanted to support for these, and it sounds like we do, which does make it a little different from other operators, right? So that's just kind of
So
interesting.
other operators also support virtual dispatch for interface implementations.
Oh, okay.
So yes, these ones can be overridden in classes, for example. Not so there is a but since these are just again, this is not a runtime concern because these are just they look to the runtime they look as regular like methods, and when if they are virtual they look like regular virtual methods, and there is nothing special needs to be done on the runtime side to support virtual dispatch.
Yeah, I guess like if you're concerned about like it being redundant to like mutate the ref and have a return type, like you could have a static thing, just take a ref for this. But at that point, I kind of see your point. Like if you want virtual dispatch, then why not just go all the way and make it an instant method?
A ref also wouldn't be valid for, well, wouldn't strictly be valid for a class. So instance methods, they always take this as one level of indirection. So for reference types, there's no extra indirection added. For value types, it becomes a ref t or an int, depending on if it's a read-only method or not. Whereas for a static method, you can either have a ref t or not a ref t. You can't have it so that it's so you're always adding one level of indirection to whatever the t already is. So there's a bit of nuance there.
There's no way to say like ref if struct, basically. Otherwise, yeah, I see.
Yeah, there is no way. I'm sorry. I was trying to describe this issue when I was talking like about defining such operator in an interface. Basically, for class, we should not allow ref, and for struct, we must require ref. So, and since the interface type is neither not known to be a class and not known to be struct, you basically blocked from declaring this the operators like that properly in an interface. Like if we say, okay, let's require ref for every type, even for classes, then we must trust the implementer of the operator that it wouldn't mutate the target. Like wouldn't provide a due instance basically at the location that was passed in by the compiler.
Okay, so back to the name of the first two. So I'm looking at the symbol versus metadata name versus if you have a named version of the operator. And well, op increment becomes increment. It looks like all the things that are op something assignment actually drop the assignment in their friendly name. So bitwise and assignment becomes just bitwise and, bitwise or assignment is just bitwise or, etc. So I assume we would say that the instance names. There's a rule that says you should not define things in terms of operators because operators have zero discoverability, so you should have friendly names of all of the things that you do. Because operators suck. They don't show up in IntelliSense. You just know they're there or you don't. So every method has the, you should, if something supports a subtraction operator, you should have an instance, or you should have a method somewhere named subtract that can be called instead. So
they do notably show up in IntelliSense nowadays.
Oh, well. Apparently times move on. But, so for, if we name this decrement assignment, I assume that the recommended instance name would still just be decrement.
Yeah, for API design, probably.
And, right, so I'm looking through the consequences of naming something. That is what we do in this meeting.
Sure, I understand. Since you didn't show this page, I just didn't know the context in which you were talking about these friendly names.
Fair enough. So, the signatures on these can't match, right? Because the static one is going to take an object, or the static one's going to take an object one, and the instance one's going to be no arg, right?
Right.
So technically, it could just be the same name.
The issue is with extensions. You need to be able to define the extension operator that should bind for for the assignment operation, or for the increment assignment, and the one that should bind for the static equivalent. in which case the signatures become the same.
Right.
So you're saying
That's
extension
exactly,
everything is what's breaking things.
yeah, exactly. This is exactly the reason why we are asking for distinct names for this, because in extensions you might run into signature conflict, like for example, for implementation methods that implement extensions, like extension that would implement an instance method, it adds the receiver parameter. And implementation method for static operator doesn't add anything, but it itself has the receiver parameter as a required one. So effectively, implementation methods collide in name and signature. So probably your guidelines for friendly names should account for that and should recommend using different names, static versus instance.
Probably
Does
not.
it make sense? Well, it's a,
Probably the answer is don't
uh,
use extension everything.
well,
The naming guidelines have
and
existed for 20 years. Extension everything existed for 20 days. So we can't go inventing entirely new naming guidelines right now. But
let me put it this way. It's your call. I don't really care what you decide there. I am just trying to explain the issue. As long as you understand the issue, I am fine with whatever decision you make.
sure. All right. So the assignment suffix, again, usually it corresponds to the equals, but what it really means at the end of the day is the value, the target changed. So in that sense, I can see assignment being a valid suffix here. But it does seem slightly different, which is why my instinct is to say something like self increment and self decrement. Steve, you've been awfully quiet. Do you have opinions?
Not really. I'm not sure how much it's ultimately going to matter because I don't. I
Indeed,
think
these
people are going to use
these,
the operators and. Sorry, go ahead.
I was gonna say these names only show up in metadata readers, so
Yeah. I don't have a strong opinion.
okay. Stefan, you asked about the feature, but you haven't opined about the name. You fine with assignment
Yeah,
here?
I'm fine. Yeah, I think it makes enough sense, and it's not super high visibility.
Yeah, and it doesn't introduce a new word that we haven't used before, which gives it bonus points. So, is this the only net new name we need? The checked pattern we have, so those are all going to be easy to blanket in. But is instance increment and instance decrement, like you've got a whole slew of operators up here, most of which aren't in this table. So
Alexei, I think we're missing unary negation, which hits the same issue as increment and decrement.
What issue? Unary negation. Well, that's
Mhm.
not an assignment operator, right? So,
Well, it modifies. It is just like increment and decrement used to kind of modify the instance. You'd want to be able to do the same operation where you don't allocate for all the same reasons.
but if I say
mm,
y plus minus x, I don't want x modified. I want a new
Yeah.
copy of x that's
Right.
data
Yeah.
returned.
Yeah,
there is no such, well, you might want to have something like that, but at the moment in the language, there is no operator with semantics that you have with operator that produces the result that you
Yeah,
that you want.
that's right. Okay.
Right, like unary negation in C# doesn't imply mutation, whereas plus plus minus minus implies that
Right.
basically
Never mind then.
that the target has been mutated, basically.
Then yeah, that should be the full set that we need.
Okay. I mean, if you're concerned about extension everything of somebody putting instance increment and instance decrement on the same thing, is that not a problem with static increment and, or sorry, static right shift and instance right shift?
Right. Like, what about all the bitwise assignment operators in the background?
Those ones already had assignment names, so they have the
Ah,
difference between the instance and the like op right shift assignment already exists in the ECMA spec.
got it.
Right, but if with extension everything, you would have the two methods exactly the same, except one says that it's an instance method and the other says it's a static method on the type. Unless the
Well,
answer is just use the static method because it works on older languages.
you can, if I understand correctly your question, you're asking what happens if you define instance and static versions of the operators in the same type. I think extensions like a separate issue, but they don't bring anything new in terms of this conflict, so to speak. So in case when a type defines both flavors, an instance and a static version of the operator, then language rules are as follows. First, language tries to apply instance form of the operator. If there is an applicable candidate, it applies the instance form. If there isn't, it falls back to look if there are applicable static forms. This is what about increment decrement. For the compound assignment, you can define an instance compound assignment operator and corresponding, like for example, you can define plus equals, and then you can define static plus operator, binary plus operator in the same type. In this case, again, language first tries to, like, if you wrote in your code like x plus equals 3, for example, then the language first tries to see if there is an applicable instance compound assignment operator, and if there is one, it applies that. Otherwise, it falls back to looking for binary plus. So, and for extensions, there is nothing much different. It's just that extensions are, with the current design proposal, extensions will be tried after like non-extension operators are tried, like if, right, and they will be applied in the same fashion. First, we will be trying instance extensions, then static extensions, and then go to the next lookup scope, repeat. So
The reason it's not an issue with like plus equals is because that has a different language syntax between static and instance. You've got plus for static, you've got plus equals for instance.
well, language applies static plus for plus equals, right?
Right, today, but I was trying to explain to Jeremy why we don't need to have a different name to avoid the extension syntax issue. And it's because there's different syntax and existing different IL names between them. Whereas for plus plus, it was the same operator syntax and the same IL name, hence the conflict.
But isn't it in bitwise and?
No, because you've got it's NIL. It should be op bitwise and op bitwise and assignment.
Right, but we already have op bitwise and assignment.
Yes, which is the language syntax and equals
Right.
versus the
And so then
language
if you-
syntax and.
But then if you define an instance operator and equals and a static operator and equals in the same,
You can't define
extension
the static
container.
one.
There is no such thing as a static plus equals. Only plus.
so how do we get the current bitwise and assignment operator? Oh, because I thought all
We don't
operators were
support it
static.
today. We don't
Well,
support it today.
C sharp, okay, just a moment.
But we
Like
named
today
it.
you can, just a moment. Today you can define, well, C sharp up to this up to this feature, C# never used those, never defined those, never defined anything with suffix assignment,
Okay.
and never used those, right? So I don't know what for what language they were added, perhaps for C++, but C# never used those and never defined methods, like never defined operators with such names. So this is the first basically time when C# tries to define and consume anything with assignment suffix.
And in C++, they're not static for the addition assignment and such. They're typically instance methods. Regular operators are also sometimes instance methods in C++. It's just how C++ works.
Okay. So,
Nothing in the spec requires them to be static.
so these names have
For
just been
IM.
sitting in this table for 20 years and we've never used them.
We've not, other languages have.
Fair enough.
Yeah.
Okay, and so then, so the instance, so is it if you make instance right shift, that's assignment?
Sorry, I don't understand the question. Are you asking what is the syntax for defining such a period, like
Is the relationship between
compounded?
the instance operators and the static operators for the suffix equaled ones that the instance versions are always assuming that they're the modifying operators? Do you define
I am
instance
confused.
operator greater than
I'm
greater than
confused
equal,
a
or do you
little
just
bit.
define greater than greater than?
You do
Okay,
greater than equals.
Okay.
Like you
I'm not-
actually use the equals in the syntax for the name.
Okay.
I'm not sure I understand the question, but let me try to answer the way I think, like the way I think what you're asking. Like you can define a compound assignment operator. In such case, you say like operator plus equals, and then parameter list. That's an instance compound assignment operator.
Right. And do instances
Or,
allow
or
non-compound
ju- ju-
operators?
just a moment. Just a moment. And if you want to define plus operator, which is static, you say operator plus. So they are using different event operator tokens in language, if this is what you are asking. Otherwise, I'm not. Otherwise, you need to clarify your question. Otherwise, I don't understand what you're asking.
Right. So the static operator is plus and never plus equals, and the instance operator is plus equals and never plus.
Yes,
Okay.
that's correct.
That was the question.
So basically the only wrinkle is with increment and decrement. Those used the same tokens, plus plus and minus minus. And yes, the instance operator plus plus would be op underscore increment assignment, and the static operator plus plus would be op underscore increment.
Fair enough. Okay. So increment and decrement are the only conflicts. And so while there are a bunch of operators not listed in this table, they're all just going to follow the pattern of assignment, except many of them actually were just already defined in the spec, and then checked as an infix if they're checked. So
Right, for other names for other operators, they're not here because we are not proposing them. They're already reserved. They're already in the ECMA 335. Right, so like
did we already do a
like
checked right shift assignment? Like I
no,
assume
there
that
is
the
no
check
such there is no checked forms for those. That's
Oh.
why we are not asking adding checked names for them. We
Fair enough.
like only for arithmetic operators have check form.
Yeah,
plus, minus, multiply, and divide.
do
So for
increment and
those,
decrement. Oh, they do. They're in that table. Never mind. All right. Sounds like we're saying looks good as proposed. How do I even copy a table? I know. I look at the markdown. All right. Anybody have anything else to say? Boop. All right. Thank you, Alexi.
thank you.
All right. The tab I opened next was Tensor Operators 112781, which sounds like it's going to be building on what we just talked about.
Yeah, so for this, some of the syntax might be a little bit wonky here and need to be adjusted, but the general principle behind it should be enough for us to get it past review here. Language is adding support for extension operators such that you can define the operators in extension methods or in the new using the new extension feature. So for each set of operators, like for example, multiplication, we have an extension that takes the relevant t self that is constrained to the tensor type. We then have the t that describes the elements contained in the tensor that is constrained to the relevant generic math operator. So in this case, I multiply operators. And then we define the signature that ends up taking the that ends up implementing the variants that we need for support here. So, for example, I multiply operators would define t self times t, t self times t self, and t times t self, matching the operators that matching the set of overloads that we have, for example, with the explicitly named tensor.multiply method. The t self should notably be constrained to I tensor, not I read-only tensor, because we want to ensure that the result can be mutable if the input was mutable. But otherwise, the signature should be mostly correct and match the principle. And then we've got it repeated for each other operator interface. So same set for addition, modulus, division, left shift, right shift, bitwise, and or XOR.
So you confused me with the read-only versus non-read-only tensor. You said the constraint should be on I tensor so that if it was mutable, it can be, but wouldn't that mean if it was mutable, it is? Like, read-only tensor is more forgiving.
Right. Yep, nope, you're right. I was thinking that read-only meant that the output couldn't be mutable at all, but that's not how we have the I read-only interfaces for collections or here. So
yeah,
the constraint is correct.
Our only doesn't mean only; it means able. So,
yeah. Yeah, readable tensor.
Yeah. Okay.
Yeah.
Okay. So you did mean read only, and
Yeah.
since it is the T self, the mutableness stays with the result.
With the T self, yes, correct. And there should, and so this is the set of extensions that we want to define, covering the full set of operators, covering the variants of taking in tensor of T, and just a T scalar where that makes sense, and including the compound assignment extensions. Again, like I mentioned at the first, some of the syntax here may not be 100% accurate. The syntax is still being worked on in some cases, and it will be adjusted to match whatever the official final language syntax is. But the idea is for these APIs with generally these signatures to be exposed, matching what the language event finalizes on.
We can't currently overload on generic constraints, right?
The new extension feature allows you to define blocks like this and make it all work.
Okay.
You will not be able to overload in the same static class on the constraint, but you can certainly define extensions that differ by constraints in different classes.
Okay.
So given that we don't see classes here, I'm not sure if the assumption that all these extension blocks go into the same class or are they go in different classes, and whether it makes a difference from your API review perspective.
Yeah, so we've not done. I mean, I've only ever seen this in a PR that Steve opened. So what are the naming? What does this turn into in the end?
What are you asking?
If I want to invoke this in static syntax instead of extension syntax, how would I do so? Well, okay, these are operators, but let's pretend it was non-operators.
If it wasn't an operator, there's so it ends up being a static method on Tensor with a particular name that you can directly invoke.
But not just named tensor dot the word that's written here.
No.
So maybe I can respond to this in more details. Basically, what we end up with is that whatever name that operator is going to be using, like for example, for multiplication, it will be, I think, open_multiply. multiply. So on Tensor, there would be a public static method called open_multiply. It will have type parameters from extension block on it. So it would be, in this case, like for the first method on the screen, it would be a generic method with all the constraints attached, like copied from the extension block. And it will have exactly the same signature as the method, assuming that the signature would refer to the type parameters on that method. So
So
T-self.
This part contributes no name?
No name to the method inside the tensor, inside the tensor class. No, it doesn't contribute to the name. So what I said that we cannot overload on the constraints, this is true for methods. So basically, if implementation methods end up having the same signature but only differ by constraints, that is not supported. So that is still not supported. But it's true that you can have different extension blocks that differ only by constraints on the blocks themselves, as long as basically the APIs that they defined inside do not collide between each other.
But this would be legal because the ref this is different than this, so the signatures actually don't. You're not actually doing signature, or you're not actually doing constraint overloading. You're doing ref overloading.
Yeah, that's different.
Yeah.
Yeah, it was just I think the question was, can we overload on constraints? That's what this is the question.
Yeah, I'm
What
just
I'm
also
assuming.
concerned with what the
Yeah,
names are, what shows up, what
sure. Yeah.
impact does extension everything blocks have on when you say tensor dot? Were these going to be a bunch of mangled names? Are they creating subtypes? If the answer is all this is invisible, and then it's
Well,
just a name here, then
extension block itself, like there are two different sort of aspects. First, implementation methods, and this is what I described before. These are the methods that become defined on the tensor class itself. Then each extension block and metadata gets a type declaration as a nested type into the tensor. That type has a unspeakable name, so to speak,
and
but
is
it's public.
hopefully editor
But
browsable
it's
never and all that.
yeah.
Yeah.
Since it has a mangled name, it's a basically unspeakable name. It doesn't show up in any IntelliSense or whatnot, but
Fair
it's
enough.
part of metadata. Since you're asking question like that, I just want to give you the sort of complete picture,
Thank you.
right? And whatever APIs are defined inside that block, they are defined in that nested type. So like looking at the first extension block, there would be a generic type with two type parameters with whatever mangled name of the type, with the constraints on that type parameters, and then exact the methods that are defined would be in that block would be defined inside that nested type. And the operator methods in particular will have special name attribute or flag in metadata applied to them. But the implementation methods for them that go into the tensor class directly, those wouldn't be marked as special name. So one effectively can consume, say, like tensor dot op underscore multiply, provide the type arguments and pass the arguments, for example, or not provide type arguments if compiler is able to infer them. So
Cool.
so
But okay. So when in the future and now I guess, but these are all operators, so their names are weird. This does not contribute to the public name at all, other than the generic. These generic parameters are lifted down to the method.
Yep.
Lifted down. That's what I said. So the copied down, I guess. Okay, so the outer class name is the outer class name, and then the name it gets here is the same, but presumably extension syntax lets you leave off the static if you're trying to make an extension instance method, or do you
If
still
you
say static this?
No, if you want to essentially the extension block is if you declarations there match what you would write inside the regular class. So if you want to declare a static operator, you say static. If you want to declare an instance operator, like the ones that we discussed just previously, then you just not say static. You say public void. Well, the signature of that is wrong. Like the static operator cannot be void. It must return the result.
A
Must
question
return
just about the extension syntax. Like
Yeah.
I see a lot of the T self there. Like, is there a name for that parameter? Like, because that's like the non. Like, if you want to access the T self, it needs to be non-static, right? And then presumably there's a name. Does that show up in the API?
So
Probably not, I
so the syntax is on the screen for multiply equals is wrong. So it should not include static modifier, and it should omit this self tensor.
Yeah, so it should be an instance method looking like a regular instance method, just
Okay.
taking the T self explicitly.
So then what does the first argument get named? Because presumably it's still making a static method.
Yeah, you're talking about implementation method.
I'm talking about when you say tensor dot. Uh, so here, let's
You
put
need to
something else.
remove,
So
you
uh,
also need to remove this parameter.
fair enough. Um, yeah, so if I do that, this in the end is going to turn into tensor.freeze. What's the name of the first parameter? This
The
at
one,
this.
well, first of all, based on the current rules, if you try to define an instance API, whether it's an operator or a method inside an extension block, the name of the receiver parameter must be provided on the extension block, like where you
That's what I was
say,
asking. So on line
yeah,
98, so there's a parameter name emitted. No, you don't add anything to the argument list there. So see on line 98 where there's like an emitted parameter, like you can only do that, I guess, because all the previous, they were all static before. But since they're not static, you just name that and then use that is what it
Oh,
looks
so there
like.
should have been a name up here.
tensor,
Because they're
yeah.
non-static methods. I think you get away without the name because they were static before. Now, I'm curious, like in this non-static case, I assume this name doesn't show up in any API. Like, do you see it anywhere,
Tens
like in
the
IntelliSense?
name of the parameter,
Yeah,
it does
like
show.
as a caller.
Well, for implementation method, for instance, extension gets this parameter as the first parameter. So since like previous example I gave previous example for static operator, right? So these are instance operators. So let me give you explain what happens inside the tensor class itself. Like
Can I ask a really quick question before the in-depth
sure.
explanation? So if I change the name of T-self tensor in this case on line 98, that wouldn't break any caller ever, right? Like I can name it whatever I want, and that's not going to affect any caller because you can't reference that name, right?
I think if they,
No,
I think if they
no,
called it in static
not right.
syntax, it would break them.
Not
If they
right.
named it.
You, this is not right.
So,
Okay.
The
Why?
significance of that name, like that name is not significant only if you have only static APIs inside the block. If you have at least one instance API inside the block, that parameter is getting added as the first parameter on the implementation method. Like specifically for multiply assign, the tensor
Got
class
it.
would,
so
yeah, for
it
example,
would show up
like
for
What
that.
Jeremy wrote. So you
Yeah.
can call it without the extension syntax, and then it does matter. So that's good to know.
Yeah, that's what I'm trying to learn, so I know how to review the proposal. So,
Yeah, no, me too. Me too. Yeah, no, so this is clarifying for me.
Right.
Thank you.
so this syntax on an instance method is exactly equivalent to that in the legacy extension declarations.
Yep.
Okay.
Which is part of the design of the new stuff is to be effectively backwards compatible, so you could rewrite existing extension methods in the new syntax.
Right. Okay. So basically, after the word extension, this part gets carried down to every instance method, and then for static methods, only this part gets carried down.
Yep.
Okay. And now I'll delete my weird insertions. And are the plus equals, sorry, are the compound assignments, are they void or
Void.
self-returning?
Void.
So the language gives it a value, but the method is void. Okay.
Right.
Like a property setter.
It's supposed to modify the target, right? So.
Okay.
And just this hasn't been discussed yet at the LDM, but again, like there will be restrictions on the receiver parameter. We need to know if it's a class or a struct. So given that T self is a class, yes, that tensor parameter must be by value parameter. But if it's constrained to a struct, then it must be a ref parameter, since it's supposed to modify the instance.
So like on line 107, it is a struct, and we have that declared. So what you're saying is that the T self that we declare on 107, not only it would need to be like ref T self
Yeah,
name
yes,
on
yes,
107. Okay.
right. So to adhere to the basically to the contract of the operator, essentially it must modify the receiver value.
And does the ref have to be declared here?
Yep.
Okay. And then Control Alt Shift down. Woohoo! That only takes like 6 keystrokes on this keyboard. Okay. So now that I think I understand the shape, T self is what we call it when it's the interface self constraint. But here I feel like we want to call these like T tensor and T scalar instead of T self and T.
That seems reasonable to me. I think we similarly call it T enumerable for link, right?
Yeah, I think they're usually T enumerable. I'll do those bulk edits over here so we don't have to watch them. And then, so this is tensor scalar, scalar tensor, and then for tensor, is it the shapes have to line up or it yells at you?
They have to be compatible shapes. So,
Fair enough.
there's this implicit broadcast that's supported. So, for example, if one of them is a scalar but represented as a tensor, that gets implicitly broadcast up to the tensor. Or if it's just a single row, then it can get broadcast up to a matrix that has rows that is a multiple of that many rows. So like a vector 2 effectively is compatible with a matrix 2 by 2.
But the number of there are things that will throw.
Yes, there are things that will throw,
and there are
if
things
they
that will not.
Incompatible.
Chat says Link calls it T-source.
I think that's because most of that takes IEnumerable T source.
Yeah.
So T source is effectively the scalar elements in the collection.
Yeah, here since, and I think most of the Link ones could have just been T because it's not ambiguous. Though maybe sometimes it's the T element versus the T enumerable, but
Yeah, I think it's because it's T source and T result in many cases.
yeah. But since here we have two T's and then naming them for what they are is seems
Yeah,
goodness.
we called it T self because that's what we called it in the other interfaces.
right, and it makes sense for the interface because it's you're applying the
Self type.
the self type
Yep.
or the what did you call it, Tanner? The curiously recursive interface declaration.
Yeah, the curiously recurring template pattern.
Yeah.
Is what it's commonly referred to in other languages.
But since this is not about self, it's actually about other. Tensor and scalar made more sense to me.
Yeah.
And we don't have named version of these operators. Going back to the
Uh,
table of names.
we already have named versions of these exposed on Tensor, so you've already got tensor.multiply.
Okay.
Um,
So this is just the adding the syntactic sugar of the operators to a feature that already exists.
right. Since we only wanted on on tensor of t where the t supports it. We don't want to be able to multiply tensor of bool, for example.
Yeah. So how does the existing multiply work? Is it just a local constraint?
Yeah, it's got its own constraint where t scalars I multiply operators.
Okay. And going back
You
to
mentioned
the... go ahead, Alexi.
you mentioned that there is already tensor.multiply. Is it in the same class basically?
Yeah, but its name is multiply, not op multiply, so it won't conflict.
Right. So effectively you have we will in the tensor class we will have two APIs doing the same thing. One is open the score multiply and the other is multiply, and they both essentially will have the same signature, right?
Yeah, but we can always editor browsable never the one here. That way users don't see op multiply in the IntelliSense.
I mean,
Well,
if
alt multiply is added implicitly by the language, and it doesn't have browsable never attribute on it, and you will not be able to apply it unless you do some kind of post rewrite for an assembly.
Attributes
So,
you put on the extension methods don't propagate to the backing method that's
but
put in
then you
IO.
will disable extension method itself, right?
No, editor
Yes,
browsable never just impacts if it's an IntelliSense. It doesn't impact if the language looks it up.
right. But that means that the extension declarations will be hidden in the IntelliSense. Yeah.
Right, but these are operators, and that's fine. If the user's manually trying to
Mhm.
resolve these, then we want them to use the method named multiply, not op multiply, because it's going to do the same thing and it's a friendlier name.
Okay, so you will have to check with IDE in terms of what behavior they have, because again, IntelliSense shows operators in
Yeah,
completion list. So I'm not sure if they going to respect the attribute applied to the operator or not. Like they
okay, yeah,
might.
that's fair.
So if
Oh,
you are betting on them not paying attention to that attribute on operator method. That's quite possible. It's quite possible this is the case, but if you want to bet on it, you probably want to double check with them and maybe even ask them to add a test so that they don't break you.
yeah, I'll sync with Cyrus.
So, looking at what you have for the current multiply, um, you have things like... I guess I need to be out of that block. That did not do what I wanted it to do. Copy. Paste. So this is one of the current multiplies defined on Tensor.
Right, this is effectively giving users a way to specify the destination so that there's no allocation required. And there's no way to do that with an operator short of doing the assignment multiply, in which case you're modifying this, where this is both an input and the destination. So if users want to if they want to multiply x and y and have a unique destination without allocating a new one, they have to use the named multiply instead of the operator.
Right. So maybe this one's a better version. I'm just saying it doesn't quite look the same as the ones you're defining the op on. Because
Right,
these weren't
because-
done in terms of the interface. This is only done in terms of read-only tensor span.
Because all of the interfaces can become the span. There's the method on the interface for getting the span out, and we didn't want to redefine or have generic explosion for a billion different. But we could have those be the generic for these if we really wanted. It just has usability considerations.
Fair. I was just going back to Steve's comment of extension methods could be floated up. I was actually expecting these were extension methods, and that I was going to say so they could be rewritten to be in the same block and look like blank, but they're actually different. So, I guess are you happy with the named versions given the new operators, or do you want new named versions as well? It sounds like you say it'll work because there's a implicit conversion to the span.
There's not an implicit conversion. There's the ability to get the read only to get the tensor span out of the tensor. So users would have to do as read only tensor, or whatever the API name was.
Okay.
Unless they're using TensorT directly, in which case there is the implicit conversion. We just didn't define the implicit on the interface because implicit conversions on interfaces are bad.
I think you said too many words in that sentence. Implicit conversions always feel nice, and then you see all the things they broke, and then you're sad and wish you hadn't added one.
I don't think you can define conversion for an interface in C#.
I think generic math added the support, or maybe it ended up getting cut, but it was definitely discussed, and we said we weren't going to use it because there was too many issues.
Yeah.
So we defined explicit named methods like create, checked, and such instead.
Right. You cannot define conversion operators in interfaces.
Fair enough. All right, so you're happy with the named versions you have. We just want these, and then you've got the blocks symmetrically, though your syntax is apparently sometimes lacking in that the instance declarations no longer look like what you thought they were.
Yeah, like I mentioned at the start, we did this before all of the syntax was nailed down for the language, and there's been some changes. So I expected some things to be a little bit off syntax-wise, and that it would need an adjustment to match the final syntax decision, but the shape otherwise matches effectively what we want.
Oh, that's not going to be a good pull replacement. You know what? I'll just leave it wrong. The fact that I then can't make the replace go back and erase the word static is gonna, yeah. Okay. But then these would actually be the equalses then, right? Just because they're on the center of the screen.
No, those ones should be actually whether these ones there should be a block that has the static ones and a separate block that has the assignment equals. My guess is that this there was a copy paste error. Yeah, and the assignment ones are there near the bottom. Just so you scroll past them.
Okay.
Yeah, and there is no this modifier on any parameter on those.
So these just shouldn't have said this.
Yeah.
These you actually meant the static. That you're defining the static shift operator. Okay. Fair enough. Yeah, I think the the sort of the grouping makes sense. The balancing of left and right makes sense. So mostly, I think this was a lesson to at least me and Stefan of how this block impacts the methods that come out. But I don't think. Oh, I guess we changed T self and T to T tensor and T scalar. Does anybody have any other changes they want to see here, or? Chat asks, what's the difference between the 2 and 3 greater than operators? Signedness, I think. Tanner, what's the difference between these two?
So the one with 2 does an arithmetic shift, which means it propagates the sign out. So a negative integer like -1 or -2 will carry the sign bit all the way through the shift to preserve, whereas the 3 is the unsigned, and so it does a logical shift and it propagates zeros in through the sign bit instead. So it's as if you had converted it to the unsigned type, shifted, and then converted back to the signed type.
And as someone who's been bitten by that, I always use unsigned types for bit shifting now. But yeah, it's the triple, which is the one you usually want if you don't know. Or it's the one that maybe makes more intuitive sense if you just think of it as a shift. Yeah. With the 0 filling in. But I don't know.
Right, because logical right shift is -2 becomes -1.
Yeah.
No, that's arithmetic.
Sorry, the arithmetic right shift is -4 becomes -2. 2 and 1 are too close to not being. They're too close to addition. And with the logical right shift, -4 becomes positive, really big number. So.
Right. Right. So if you're treating the thing as just bits, you want the triple. But if you're actually like trying to emulate like powers in math, then maybe
if you use this because you're like, this is faster than divide.
Yeah.
If you thought divide, you wanted this one, and if you thought bits, you want this one.
Yep.
Yeah. Okay. So yeah, I think we're good on this one. Unless anybody has anything else.
Notably for any listeners, don't do arithmetic shifting instead of divide. The JIT does that for you.
But I'm old.
Don't
Tanner.
write complicated. Yeah. But if anyone was thinking about doing it for perf, you don't need to. The JIT will do it for you nowadays. So just write what is natural and readable.
All right. Sold. Or, in the words of, I'm going to say Twain, which probably means it's not Twain. It was right when I wrote it. Blame the editor. All right. Now, is dense, sparse, and contiguous? 111, 9, or 64?
Yeah, so essentially we have, and I'm going to let Michael step in here and do a little bit more of the explaining here in a minute, but the summary is we have a set of properties that all tensors can have that we want to expose to users. The there's some common terms that get used throughout various ecosystems, including sparse, contiguous, dense, and linear. What those terms exactly mean sometimes depends on the framework you're working in. So we have proposals for what each one means for .NET and some descriptions of and further down there should be some descriptions of what they're commonly referred to as in other ecosystems. And while all ecosystems have a general agreement on what some of the concepts are, some things like sparseness or denseness are a little bit variable between them. And so, Michael, I'll let you take over from here because you did most of the research into exactly what other ecosystems do there. Um,
So, right, basically the idea behind this is to give, I mean, we need to know it internally, but to give the user some sense of how the data is stored, right? Whether it's all, if I have 4 elements, whether all 4 elements are represented, whether there's less than 4 elements, and we're doing some type of broadcasting, so on and so forth. This helps us for optimization purposes. It also lets the user know whether they, if they're about to do some computationally expensive stuff, it might be advantageous for them to go ahead and make everything be a one-to-one representation between the backing memory and the number of elements it represents. And so that's the idea behind why we want to expose these. As Tanner mentioned, there's various terms that are floated around that yeah, okay, I'll just get into them, I guess, right? So first thing, the initial thought we had was to use is sparse to represent when you don't have a one-to-one relationship between the source and the data. Whether you have that's one element that's being broadcasted up to X number of elements, or something like that, or whether you take a slice out of a larger tensor and now your subtensor, your slice tensor, right, has gaps in between the data, things like that. But sparse typically in other tensor frameworks is used to represent very specific formats where you typically have lots of one number. Usually it's lots of zeros, but it could be any number. And so it's used as a space-saving format. And that's typically how sparse is used. On the flip side, when they want to represent that a tensor is not one-to-one between the backing data and how many elements it represents, they will mark it as a view. So they will say this is, is view will return true, right? And then dense represents that everything is a one-to-one relationship between the backing memory and the elements that are represented. Basically, we want to expose the same type of metadata, but we're trying to figure out the names that would be correct for our implementation of tensors. So for example, we've talked about views before, how we don't really use the word view, right? We use span, but that doesn't necessarily work well in this case because it's not necessarily the underlying data is a span. It's trying to say that it's not a one-to-one relationship between the two. Yeah. So the idea, right, is just to figure out what we actually want to name those things. So the ideas that we came up with were these, 5 right there, or 4 with then the 2 dense tensor method there. The is sparse one we weren't sure on just because, like I said, that has such a common usage in other frameworks. And if you Google what a sparse tensor is, it will basically tell you. In fact, in Microsoft's Onyx runtime library, they use this sparse the same way as everything else to represent that it's a space-saving format.
So you said you're not sure about it, but you're still proposing adding it. What does it actually do?
So we weren't sure on the name. That's why we wanted to discuss it with everybody here. I think personally that isView is better, but that doesn't really jive with the other, how we've been naming things in the past. But we do need to have this flag, or this. We need to have a way to expose this to the user.
And it's not our interpretation of it is not the opposite of is dense.
The common interpretation of is sparse is not the opposite of is dense. The common interpretation of is sparse is a space-saving format where you can say 90% of my values are 0 and the rest are something else.
And what is the
Whereas-
definition of is dense?
Is dense is that it's a 1-to-1. But if you had data behind the scenes, like say you had a 1-by-1 tensor, or you had one element in your backing data, and you said it's actually a 2-by-2 tensor, and you're just broadcasting that one value to the other, to the total of 4 values, they would not say that that's a sparse tensor. They would say that's a view, because sparse is specifically reserved for when you're using, there's like 4 different specific formats for space saving purposes, not to represent that the backing data does not match 1-to-1 with how many elements the tensor represents.
What's the
When
use of
would
knowing that's
something-
sparse?
If you're doing something that's computationally expensive and you have sparse data, a lot of the time you cannot take advantage of any optimizations, because, for example, you can't use a lot of SIMD stuff because you can't just pass in, right, you can't just pass in a span because you only have a single element, right? Or you have gaps in the elements when it needs to be dense for taking advantage of a lot of those optimizations. So for computationally expensive things, oftentimes it's better for the user to turn the sparse data into dense data and then run all those operations.
Sorry, but you said sparse and dense aren't opposites. So I'm asking, why would you want to know? I am a tensor that is 99% zeros, and I have one non-zero value somewhere in me. Why would you want to know that, unless you're the thing that's actually supposed to like serialize it?
So because the user needs to be the one to decide if they're going to densify that or not.
But that's his dense.
But that's why I'm questioning that. How is it not the opposite if the answer, if it is true, is to turn it into the other thing? Doesn't that mean that they're sort of two sides of the same coin?
Yeah, but it's more like a 3-sided coin, because you can have something that's not. So according to the standard interpretation of is sparse, you can have something where is dense is false and is sparse is false, because it's not one of those specific is sparse formats, but the data is
Right.
not dense.
But it can't be both, right? It can't be sparse and dense.
Correct.
It could be
It can't-
not sparse and not dense. But this implies that it's like probably shouldn't be 4 bools, which has 16 possible states, right? Could we? I don't know. Like, can we collapse these a little?
Well, but again, I'm asking why someone would want to know is sparse is true. You've told me cases where they want to know is sparse is false. Or no, wait, maybe it's, but like everything you've described of when they want to know the answer is they want to ask is dense, because if not is dense, then they want to call to dense tensor. So why do they want to know if is sparse is true?
So we don't have some of this stuff exposed right now. It may be, down the line at some point, but there are situations, for example, if you want to transmit a tensor across the wire, right? If you have data that is appropriate for doing sparse data, you may want to sparsify it and then send it across the wire.
But then you would need more data than just am I sparse? You would need to know how to serialize it, which is a different problem, right?
Yeah, if right now we don't support any of those specific sparse formats. If we did, we would have to figure out, right, how we want to track what format it's using, so on and so forth.
At which point I still don't know what the value of the Boolean on the interface is.
Yeah, the most important one for us, right, is knowing whether it's dense or not. Dense, and then depending on how we define contiguous or linear, right, those ones would be important for us because it will let us know how we want to do optimizations.
Is everything that's linear contiguous? I'm just curious. Like, I'm trying to understand what they all mean.
No. So,
Okay.
so I
So
think
it
the
just
answer
means
to
it's a lie.
Jeremy, I think the answer to Jeremy's
Single
question is we
dimensional.
don't actually need is sparse today. We can cut that and save it for later. So, there's kind of this threefold question of is it dense, contiguous, and linear, where because for example, I gave the example of the broadcast scenario earlier, where you can have a two a vector that has two elements in it, and that is compatible with a matrix that is 2 by 2, for example, or something that's 2 by 2 by 2 or some other shape. Because you're just replicating the two rows again for every higher dimension. In that case, you have contiguous data, and the data is linear in some senses, but you don't have all elements present. And so there's this so the general concept you want to be able to answer is what data can I access contiguously and safely? And are there any gaps between the data? And so for example, you can have in the normal sense of an array, you have data that is one element apart. But with tensors, you don't actually have to have elements that are one apart. You could have a buffer that is a backing buffer that is 16 bytes big, and you could be taking every fourth byte from that, in which case the base stride would be 4. And so in that case, you've got a backing buffer that is dense, but the actual tensor data that you're representing from that buffer is not dense. It is not contiguous, and it is not linearly indexable like that.
So I guess what's weird about this, right? Like aside from is dense, which apparently for like, you might look at that to call too dense tensor if it's not, and you need it to be dense for reasons. Like if the only way to observe the linearity of it or the contiguousness of it is like via these booleans, like shouldn't it just kind of be an implementation detail of the operators? And like, let me see if I understand linear right. So you're saying that it can be more than one dimensional and be linear, but then that each dimension is just a repeat of the vector, basically, like in every dimension, like it's a
Right.
single vector that's repeated. Yeah.
So you can have something that has 16, where logically you have 16 elements, but physically you only store 2 of them.
But why does that
and
matter?
those 2 is repeated. Well, because when you're going to so if you're trying to do direct access of the data in any fashion, which is very common for tensor data because of all the dimensionality and the costs, there's many cases where users will hand iterate the data. You need to be able to know how you safely access the data. And so internally, we're already tracking flags for this data, and we're already using that ourselves. And users need the same data so that they don't have to constantly compute it from the available strides and length information.
Got it. And in the case of is linear, like maybe you could check, but that'd be like very computationally expensive. But you might just
Right.
like you could just check every
And so kind of like is linear is mostly meant to be, are all the data elements there linearly indexable? So it's logically a concept of does the length of the backing buffer match the number of elements represented by the tensor? So something that has 16 elements in the backing buffer and 16 elements in the tensor is linear, because there's no chance that doing a linear address computation from inbounds indexes will access something out of range. Is contiguous is used for when the base stride is effectively 1. So that means that sequential elements exist side by side for up to a row of data.
I see. So the rows
Potentially.
don't have to be contiguous. So
Right,
it's like
you can
within a
have
row, it's contiguous.
Right, but you can have gaps between the rows potentially. And so you've got those two concepts of can I effectively get a span out from the backing buffer, and can I access data correctly using the linear index, or might I end up accessing something out of bounds because I actually have to be repeating access to the data instead and not offsetting the stride, because the stride's effectively 0 in that case.
would it be possible for is contiguous tensor to have gaps between the rows?
Michael, do you remember if that's how we have it right now? I think
I
for-
think we said, yeah, I think we said yes. It's like is dense. So like is linear is the strictest condition, right? Where it has to be 1-to-1 for everything. Is contiguous was like on a row basis, as long as you have contiguous memory, then that would be true. So if contiguous is true, then is linear is true. But if is linear is true, is contiguous does not have to be true. And then is dense is like the lesser strict constraint. I believe
You could imagine, right, like an in between of is linear and is contiguous, where it's like it doesn't have to be linear. Like you can have different data in each row, but like you can't have gaps between rows. Like, does that matter?
That sounds like you just described something that is linear.
Oh, so linear doesn't mean that you're repeating the exact same vector along like every possible,
Right.
like in a certain direction.
If
Okay.
there's broadcasts, then it's not linear because you cannot strictly take your indexing and access all of the data linearly effectively. You can't just like increment from I to flattened length and access all the correct data.
I see. So is linear is basically is really contiguous, like between rows and stuff. Like you go if the iteration order, you just go forward in memory. Okay.
But
Whereas
contiguous could be true if you have 16 contiguous bytes representing a row, but then skip 32 bytes before you hit another 16 contiguous bytes representing a different row.
Correct.
Sounds like it.
So you are contiguous, but because there's a hole in your you don't just have a start address and an end address and everything in between is part of your tensor. You're not linear.
Yeah.
Okay. Are
Maybe
you dense?
Maybe a better name for that would be like has contiguous rows or something like to that effect.
Yeah, I don't mind that. It seems pretty.
Because what your description of is linear is what I would expect is contiguous to mean. Of that.
Or has linear rows, right? Like if we just want to stick with the same terminology.
Or maybe instead of is linear, we could also give it a name of like, just shooting out a terrible name here, is backing buffer flattened.
And here I was just thinking
strictly
is
one-to-one.
hypercontiguous. So
Is hypercontiguous.
yeah,
Ship
it tells you it's more contiguous-y.
Maybe is contiguous and has contiguous rows to differentiate, and if something is contiguous, everything is contiguous in it. If has contiguous row, and so something that is contiguous will always have has contiguous rows be true. But you can have has contiguous rows be true without being fully contiguous. So you could have that one be true and is contiguous be false.
Do contiguous the things you're currently calling contiguous, dense, and linear, do they always have a hierarchy? Certainly two of them do. Does dense play in that hierarchy as well?
A little bit. Dense, I don't think we have fully. I don't think we're actually using that one internally right now. We used the term is contiguous and dense internally to mean that the flattened length and minimum linear length are the same. So fully to mean fully contiguous effectively.
But that's linear.
Yes.
Yeah,
we
I
hadn't
think we can remove
adjusted
one of
we
those.
hadn't adjusted
Sure.
the internal name to be linear yet.
Fair enough. I'm just wondering if these three booleans are really an enum of I'm not even dense, and then I'm dense, and then I'm row contiguous, and then I'm fully contiguous.
Then enum could work, yes.
It would have the slightly tricky problem of you're presumably going to start it off with an ordering, and if you ever come up with a fifth thing, then your ordering semantics are probably going to be broken. But
Yeah.
and then sparse is a completely different access. It sounds like.
Yeah, because sparse is like a lot of sparse tensors are implemented effectively as like dictionaries, where you'll have an array of valid indexes, and then you'll have the backing data, and you might it's basically a two-dimensional lookup to get the data. That way you don't have to store all the data that doesn't exist. It's just implicit
Right.
based on if the if exists check passes.
And if try get value returns false, you return 0 because it was
Right.
in your
Yep.
tensor bounds, but not in your memory map or whatever you want to call it.
Yeah.
So
Yep.
yeah. So I mean, I know I just now proposed an enum for describing the states. We can then say that while it's possible, it's a bad idea. For again, it's not really semantic. You can't insert a middle state in it if somebody wants to do greater than or less than on it because it's an integer value. But at least understanding that there is a hierarchy is, I think, useful for me.
One, and if we're gonna change the name isDense, then we should probably change to dense tensor. The only reason I'm hesitant to try to want to change isDense is just because of that is like industry standard term for tensors. And basically, right, they're using isDense to basically mean islinear, right? It's a one-to-one relationship between the backing data and the representation of the data, and you could iterate through it.
Sorry, I know we've been over this, but what's the actual difference between dense and linear to us?
Yeah, I think so. I think that it got pulled up here because internally we had isDense and contiguous, and then we decided to switch some to linear, and we were in the process of that when I made this API proposal. I think that's why they both got pulled up.
Yeah, the weird nuance here is that dense kind of mean like Michael was saying earlier, it kind of means two things. So some people use it to mean the opposite of sparse. So you've got something that's sparse or you've got something that's dense. And other people introduce this third concept, which is view. And so in their case, they've got sparse tensors, they've got dense tensors, which effectively means linear, and they've got views, which means that it can be nonlinear. There can be gaps between the rows of any magnitude. And so they don't track necessarily if there's contiguous elements within that view. We have tensor spans to represent views. And so we don't necessarily need that concept, and we have to make the decision of, does dense mean the opposite of sparse in .NET, or does dense mean effectively linear? If it means effectively linear, then two-dense tensor is removing any implicit broadcasting. It is removing any sparseness, if sparseness existed, for let's say an Onyx sparse tensor that implemented iRead-only tensor. If we said that it's just the opposite of sparse, then it just removes sparseness from the tensor, and it can do that however it thinks is most efficient. And so that's the decision we have to make.
Yep.
So
to add on,
so we don't need isDense and islinear. We should be thinking of those as the same thing, as like an option of like what we call it. And then we change the name of two dense tensor to two linear tensor if we wanted to change it. Am I understanding that correctly?
Well, if we decided that dense means the same as linear.
Okay, what could it mean
Instead
if
of the
not
opposite.
linear?
yes.
Well,
Instead of just not sparse. So in other words, dense could just be has contiguous rows. I see. Yeah,
Yeah.
let's make it. So in other languages,
Yeah.
it means has contiguous rows, basically.
It
No,
depends on the language.
Yeah, it depends on language. In PyTorch, which is probably the biggest one right now, right? Is dense means is linear with what we were talking about here. It means the backing memory is a one-to-one mapping. Then they have is is view, which is what we're talking about, like has contiguous rows here, where or not even has contiguous rows. It just means that like it's not a one-to-one mapping, but it's not the specific sparse format of like the dictionary stuff that Tanner was talking about. And then they have is sparse, which is those specific formats where you are space saving. So those are the three that they have. Now,
Right,
Tanner was saying, right, that we kind of are using spans to represent views. The only caveat to that is with Tensor, with a Torch Sharp's definition of a view, it just means that the data is not one-to-one, right? It's not, the backing memory is not one-to-one with the elements that the tensor represents, which we can represent in a tensor as well. So it's not just that tensor spans are our view, it's you can have a tensor that essentially represents that same concept of a view as well. So that's the other thing that's kind of floating in the mix of this.
Okay, since we have 10 minutes, how about this? We keep is sparse. It means you have one of those special sparse formats. It's space saving. Doesn't necessarily mean anything else other than that. You have has linear rows and is linear, and forget anything about density because it doesn't seem super well defined, and people would expect it to be the opposite of sparse, which it's not. So we stick with the linear naming and call it two linear tensor.
Is an embedded. So normally it's just used for broadcast, but because if we're saying that it's for space saving in general, then is an embedded broadcast sparse?
Good question. I don't. If you can make a good decision there, I'm fine with it.
I would say no. I think that if we want to go that route, we should reserve sparse for those specific sparse formats. There's like 4 or 5 of them. That would be me personally. I also I would lean more towards keeping dense as opposed to linear, just because that is what everybody in the industry uses.
But
I
see. But so in this world, though, you would use dense to not mean linear, so you keep dense.
Dense they use dense to mean linear. They don't necessarily mean dense to mean is not sparse, because they have the view, right? They've got a 3-state thing. It's not a Boolean, but they use dense to mean is linear. You're right. It's you can iterate through it linearly, and so when it says is dense, you know that that's the case. And when you do two dense tensor, you know that it's going to copy the data to make it a one-to-one relationship.
Yeah, it's kind of this issue of PyTorch decide. So there was stuff before PyTorch, and terms before PyTorch, and a bunch of different libraries did things. PyTorch became the most popular one and chose for there to be is view in addition to is dense. And PyTorch being the number one, many users, but not necessarily all users, expect dense to mean linear. But many libraries that existed before PyTorch and some that existed after still have is dense just as the opposite of sparse. And that's one of the problems.
And by linear, we mean that everything is contained within contiguous, or everything is contained within contiguous memory, and there are no don't care values in the memory. Or rather, there are nothing. If you painted every element and you assigned it, and you XOR'd or you tilted every element, every bit of contiguous memory would change.
Yes.
Okay.
So the backing buffer, the backing buffer could be iterated from 0 to flattened length.
Yeah.
And you would not access any data you shouldn't.
And you would access all data
you
should.
Access all the data that you should.
Yes. And you would access all the data that you should.
All right. So you said PyTorch has is view. Would that be basically, is that true when it's linear? Or is that only when it has contiguous rows, but is not linear?
So, yeah, is view is for when the backing data and the number of elements represented don't match up, and it is not the specific sparse formats.
So is view, using these APIs would be like so. If I were to try to write the equivalent of PyTorch is view using these APIs, it'd be basically not is linear and is contiguous or is contiguous rows. And
It
then
doesn't
of
even
course
have
that
to be
would never be
contiguous
sparse.
rows. It doesn't even have
Okay.
to be contiguous rows. There's right. It's just all the guarantee that you get is that it's not one-to-one between the backing data and the represented elements,
Right.
And it's
so,
not sparse.
So
and it's not
linear
sparse.
linear means flattened length is the same as the backing buffer length. View in PyTorch means that the backing buffer length is not the same as the flattened length.
And you have no guarantees about whether anything is contiguous within that or not. That's what you get, is that it's not the same. And they don't expose anything to the user about whether rows are contiguous or not.
But
Right.
can we not expose that? If PyTorch doesn't have to expose that.
Yeah, we don't. So we need it internally, right? But that one does not need to be exposed. What needs to be exposed is whether it's dense or not, whether it's dense, whether it's not dense. Those are like the two most important things of all those things here. Is whether they can iterate through it linearly or not, basically.
So it sounds like you want is dense because that's a very, very strict thing, and then maybe has dense rows, meaning there are slices you can take that is dense will turn to true on.
We don't need that though. PyTorch doesn't have that.
We are also quite a bit more advanced in our memory access APIs in general in .NET than PyTorch is. I think it's something that we do want for our users.
We could add it later though, right? Or is this
It's on
No.
an interface.
it's a new interface and we're not going to do DIMs? Okay.
Well, I don't think we could do it. Well, I guess
We
we
would
could
have to
just return
throw
false
an
and
is. It would
customize
be
and-
terrible. Yeah.
Or the
like,
dim would have to
has
just
the
say false,
capability.
and then
Yeah.
but then it would be wrong
Sorry,
sometimes.
everyone was talking over each other. Why couldn't we do it, Dim? What was the explanation?
We could. We just end up returning false and pessimizing.
Right.
But I think if we just went with is dense and has dense rows, I think that would be sufficient there. And we document that dense means the same thing as it does in PyTorch, which is that the backing, store, and the flattened length are the same.
And you drop is sparse for now.
Yeah, we said
Or
it
you
didn't
keep
have a
that too.
purpose.
Okay.
Yeah, cause we don't implement or do anything with sparse formats yet.
Okay. So that we could add as a dim maybe, and just default to false if we
I mean,
later add
Yeah,
sparse support or whatever.
but it feels like if is sparse was true, there are questions you'd want to know, which suggests that it would be
Mhm.
coming with something like an I sparse tensor. At which point, is
Fair
sparse is this an I sparse tensor?
Yeah, that
So
makes a lot of sense.
And then-
Okay, I mean that seems fine, I guess, right? Like has dense rows, is dense, and two dense tensor.
Yeah, I think so.
Yeah, so we've said has dense rows, and that makes sense when you're in a two-dimensional thing. When you're if you're in like a six-dimensional tensor, is rows mean one dimension down? Does rows mean the second to last dimension? Like, are we throwing in a word that doesn't make sense in the domain?
Yeah, that's the hard part. Generally, row represents the generally you think about it as you've got scalar values combine to form rows combine together to form matrices or images, and then you have batches of matrices or images on top of that. So that's typically how it's viewed, but not necessarily how it always is viewed. But memory is also described as row major access and things like that. So I think row is sufficient enough there.
Did we say
in the
vector?
general context of the memory model?
Would it be wrong to say has contiguous vectors? Like the rows are vectors. right? Ish.
Yeah. Yeah, if you just described it abstractly as 0 dimension is scalar, 1 dimension is vector, 2 dimension is matrix, then that would make sense.
Yeah, I don't know if like that's the terminology we use. I mean, C++ uses
Yeah,
this mean list, which is kind of similar.
yeah, mostly you just get like, oh, it's a 1-dimensional tensor, oh, it's a 2-dimensional tensor, oh, it's a 3-dimensional tensor. I don't think they really um, talk about it in specific terms like vector or matrix or whatever.
As contiguous single dimensions. Yeah, I mean that's a little wordy.
Maybe Tanner, maybe you and I could reiterate on that and bring it back, because I guess the other thought that we could do is, instead of having a bool of is contiguous, we could return the smallest dimension that is contiguous and change, instead of being a bool, it could be the dimension number that's right, the smallest that's contiguous. But
We could describe it as simply we could describe it as simply has any contiguous elements.
So has contiguous elements, or has
Yeah.
has any contiguous elements would probably be a better name.
or instead of elements, we want to do dimensions.
Oh, yeah.
Has any contiguous dimension. So that dimension is contiguous.
Sure. If you need it at all. That seems okay.
Or we could say has any dense dimension.
Oh,
If we wanted to reuse
to
that.
reuse the word. Yeah, it's better in that case with all the qualifiers. Has any dense
Right,
dimension.
because that does say if you take the sort of for each child tensor in my tensor, that at some point you find that from here on out it's turtles all the way down.
Yeah. So if you think about it as has any dense dimension, then basically how it would work is dense represents is the entire tensor dense, and has any dense dimension is effectively if it means that for each dimension in tensor dimensions, one of them will return true if you check dimension is dense.
That seems a lot. Yeah, I don't mind that. That seems a lot more comprehensible.
Okay.
Basically, it's an optimization instead of doing the link equivalent of tensor dimensions, any tensor equals greater than tensor dot is dense. So it means we can cache it in everything, and it works nicely. Yeah, I think that makes sense then.
Okay. So for the last member, I read only tensor to dense tensor is returning an I read only tensor. Is the expectation that classes are going to use the more specific return decal, or does that not work for interfaces?
Use the curiously recurring template pattern. But I doubt we want to.
I think
I
what we're
read only
missing.
tensor of T cell.
I think what
Return
we're
T-cell.
missing here is I think this was open before we had I read only tensor and I read only tensor of T, and so the pattern has been we would also have public interface I read only tensor T self T, and then that would have T self to dense tensor.
Okay, so it is the curiously recurring template pattern.
Notably, if we have two dense tensor here on I read only tensor, it'd be the only API on the non-generic interfaces that returns an interface, and it would prevent us from ever implementing the interfaces on the ref struct types. So we could never implement I read only tensor on tensor span, for example.
Okay, so you don't want it on I read only tensor. You want to move it to the I read only tensor of T self and T.
I think so, unless Michael has a problem with that.
I don't think so.
So you want that.
Correct.
Yeah, I mean, right, technically we wouldn't need it to be there from like just the actual functionality terms, but if it's going to cause problems with the structs with the interfaces, then we should do that.
I see. In the generic one would implement the non-generic one.
Yeah,
it
it
does.
already does.
Okay, got it.
Yeah. And sorry for the confusing terminology here. Michael and I tried to get everything laid out, and these terms are just not fun.
All right. So are you happy with has any dense dimensions?
I am.
Yep.
All right. So is dense is the highest dimension dense. Has any dense dimensions means if you go to the bottom dimension, it will say it is dense, and maybe some other higher ones will also say is dense.
Yes.
Yes.
Okay, and then to dense tensor, if it is dense, is it allowed to return this for a mutable thing, or is it always supposed to be a copy?
It can return this. All of the APIs try and avoid allocations where possible.
Okay, so a mutable tensor that is not dense and you call it a dense tensor means you now have a copy, and if it returns is dense to dense tensor can return this, and so mutating it is caveat emptor. Okay.
Yeah.
Yes, if you missed it, Steve, I did the intro on Latin today.
On caveat emptor, I missed that.
Well, I said
You
caveat
did
emptor,
miss
which
it,
reminded me
but thanks for following up.
reminded me that I did the intro in Latin today
Oh, I see.
because Steve asked for it.
Well, I was more questioning whether you ever had or not.
And now I have. All right, so I think we're happy with this. So is contiguous is gone, is linear is gone, is sparse is gone. We just have is dense and two dense tensor, and then the middle ground of there's density in here somewhere.
Yes.
All right.
And that gives us room to do the optimizations for users to convert if they want to avoid memory lookup costs, etc.
And here I thought I was being cynical when I only put 3 items on the agenda.
And we're still over time. All right. See everybody.
Yep. And but technically, technically the window scrolls. There's no item below the fold. It's just padding. So we kind of got rid of the scroll bar. We kind of hit our goal.
You could always change your scaling.
And Steve dropped.
Oh, he's gone.
I was going to ask. I think the vector data abstractions we just need to mark as unready for review, but the fact that it was tracking a thing from a different repository confuses our process. So, all right. Well, so that was vectors. If anybody still understands contiguous and linear and dense, well, I'm sorry because we got rid of all of them and they're now just called dense. And with that, thank you for joining us, and we will be back next Tuesday at our same .NET time on our same .NET channel. And until then, sayonara.